Magic water?
Hey, do you believe that I know a magic?
Huh? What? What magic? How come cannot?
Huh?
Cannot lah!
Huh? You don't believe me?
No.
Then I show you the magic. 是啊。
哇！ Wow!
Oh my god, what is this? Oh my god, how can you do this? You really can do the magic? Can you teach me? Please teach us.
Let me explain the supercooling.
Is supercooling a magic or science? Now, let me introduce about the supercooling. Supercooling is the process of cooling a liquid or a gas below its freezing point without it becoming a solid. Supercooling during the liquid-solid phase change is the phenomenon when a material's crystallization initiation occurs at a temperature below its freezing temperature. It's usually at 0 degrees Celsius. How does the supercooling work? This is because the lack of nucleation sites. The inside of a soda drink is very smooth and clean. There are no scratches, dust particles, or impurities for the first ice crystal to easily form on. The liquid is so pure that the molecules can't get started forming a solid. There's another reason is stillness. If the refrigerator is not disturbed, the cola remains still. If there is a movement like jostling or shaking, can provide the necessary energy for molecules to clump together and start the freezing process. Now, let me teach you how to make a supercool flutes. First, carefully place a purified water or a carbonated drink into the freezer. Next, wait for 3 to 4 hours. It depends on the refrigerator efficiency. Then, after the time is up, gently open the freezer door and take the bottle out. Last, shake the bottle and open it. Then, the supercooling process is occur.
Now, let's look at a real-world example of supercooling, which is the famous Thailand shaky cook. In this video, you can see a glass bottle of Coca-Cola placed in a bucket filled with ice and salt. The salt helps to lower the freezing point of water, so the mixture becomes much colder than 0 degrees Celsius. Because of that, the Coke inside the bottle gets super cool. It is cooler than its freezing point, but it still stays as a liquid. When the seller opens the bottle or gives it a small knock, the pressure changes and bubble forms. These bubbles become nucleation points, and the Coke instantly freezes from top to bottom. It's turning into a slushy drink within seconds. Another example of supercooling happens naturally in our atmosphere. Supercool water droplets exist in clouds, and they can stay liquid even below 0 degrees Celsius. When these droplets touch dust particles or ice crystals, they freeze instantly. This process leads to the formation of snow or hail. So, supercooling doesn't only make cold drinks, it also plays a role in creating weather phenomena around us.
Another most serious situation is airplane icing. When airplanes fly through supercool clouds, the tiny water droplets inside the cloud are below 0 degrees Celsius but still in liquid form. The moment when tiny water droplets touch the cold surface of the airplane wings, they freeze instantly, forming a layer of ice. The important thing is that this can affect the plane's aerodynamics and safety, so aircraft need special de-icing systems to prevent this. Supercooling is also used in industries, especially in food preservation and cryobiology. For example, in food storage, supercooling allows companies to keep meat or fish at very low temperatures without actually freezing them. This helps preserve freshness and extend shelf life, and then freezing can be triggered in a controlled way when needed. Of course, our experiment didn't work perfectly the first time. We faced many challenges along the way. Sometimes, instead of staying super cool, our bottles froze completely, so we couldn't trigger the freezing effect later. We also tried use tap water, but it didn't work at all, because impurities and air bubbles in tap water make it freeze earlier. And if we move to shake the bottles too much before testing, that can trigger freezing early too. Here's a short clip of one of our failed attempts. You can see how the water froze inside before we could trigger it, which shows how sensitive supercooling actually is.
Tap water usually feels to supercool because it is not completely pure. It contains impurities and minerals that act as nucleation sites, or tiny crystallization seeds, where ice begins to form. These small particles cause freezing to start earlier before the water can actually become supercool. In addition, tap water contains dissolved gases and microbubbles. When the temperature drops, these bubbles can easily trigger ice crystal formation. That's why tap water often freezes gradually instead of suddenly turning into ice at once. As a result, the freezing behavior becomes inconsistent. Sometimes it freezes from the edge, sometimes from the center, or just gradually. It won't remain liquid until triggered like pure water or cola in our experiment. So that's why it is much harder to see a clear supercooling effect using tap water.
In conclusion, supercooling may look magical, but is actually an amazing demonstration of physics and chemistry working together. It shows how temperature, purity, and molecular structure all interact to create something fascinating. So next time you see water instantly freezing, remember, it's not magic, it's science. Thank you for watching our videos.
Hey, I know on what magic? 哇！